Hello, YouTube faithful, and welcome to the Princeton Review's SAT Night Live. My name is Ken Brenner, here to guide you through tonight's topic about all things SAT. And what we're focusing on tonight is something that affects us not just on the SAT, but in life in general. When we take on a project that winds up being quite a bit more than we can chew. On the SAT, there are a ton of different types of math problems, but nowhere are the problems more intimidating and time-consuming than on word problems or any math problem that involves multiple steps. It just feels like when we're given this 10 or 15 line word problem that references all these different facts and figures and background information, it's easy to spend a long time and feel like we put in a lot of work to maybe get 1 point. And so tonight we're really going to talk about what do you do when you're in the middle of one of those very time-consuming problems with tons of different steps. And the main thing as we look at our first sample problem is going to be a core technique that we like to call bite-sized pieces. Bite-sized pieces are based off of this idea that whenever you're confronted with a lot of work to do in anything, you should handle it one step at a time. If you look at the first problem, question number 6 that's on screen right now, you might be tempted to read the entire problem so you can know what's going on. But if we do that, we're going to often get very caught on the math in the problem. And it's almost like we're going to start solving things before we even know where we're supposed to wind up. So let's not do that. It's almost like if you were planning a road trip, you would pick the destination before you started driving. So what we're going to do is we're essentially going to ignore most of the text in the problem, and we're going to jump to the final question. If there are a total of 75 candy-coated chocolates in the bowl, how many of them are not yellow? Now I understand where I need to wind up. The pieces of candy in this bowl of candy that aren't yellow. I want to go through this step one step at a time. Through the problem one step at a time, right? And as a matter of fact, I noticed that in my answer choices, I get 4 options for the not yellow pieces. The not yellow pieces are either 10, 15, 55, and 60. What I might be able to do is use one of these answers and work it against the problem. It's a concept we'll go over in later videos called plugging in the answers. I might say to myself, let's pretend that there were 55 pieces of candy in here that were not yellow. Now, since there are 75 pieces of candy, that would tell me that if choice C is right, there must be 20 yellow pieces of candy in the bowl, since 55 plus 20 is 75. Okay, good. Now, I can go in the problem and find the piece of information that's about yellow candy. There are half as many yellow pieces as there are green ones. Okay, well, then I could say, I could work on my green pieces of candy. My green pieces of candy, since there's half as many yellow as green, must be 40. So far, so good. Where does the problem talk about my green pieces of candy? It says there's 3 times as many green pieces as brown ones. Well, if there's 3 times as many pieces as brown ones, then I would say brown would have to be 1/3 of 40, or 40 over 3. Oh man, I've run into a problem. I really can't have pieces of candy. So I've gotten through only some of the work in the problem, but I already have the sense that choice C isn't going to be right because based off the problem, these chocolates all need to be whole. They need to be integers. So I'm going to say, you know what? C is not right. But based off what I read, it doesn't seem like there should be that many yellow pieces. So maybe now I'll try D. If there were 60 pieces that were not yellow, there's 15 pieces that are yellow. After all, we're looking at 75 pieces of candy. Now, 60 and 15 is 75. If yellow is half as many yellow as green, green would be 30. If there's 3 times as many green as brown pieces, brown would have to be 10. And finally, if there's twice as many red pieces as brown, red would have to be 20. Do these numbers work? 15 yellow pieces plus 30 green plus 10 brown plus 20 red equals exactly 75 pieces. And there are a total of 60 pieces that are not yellow. The answer is D. I actually wound up never really reading every word of the problem. I worked the problem in bite-sized pieces, one step at a time, until I was able to get to an answer. And so that's going to be true for so many multi-step problems. Let's do the most straightforward looking piece before we worry about doing the rest of it. Take a look at this next problem. There's a lot of information here, but I'm always going to start my bite-sized pieces by reading the final question. And the final question here is, which of the following represents his total charge in dollars for that period of membership? And I know from the answers that I want some type of equation that is that membership charge. You might say to yourself, well, now I need to build the entire equation. And that's true. But watch what happens when you build it one step at a time. The very first thing the problem tells me is Anthony's Taekwondo class charges a monthly membership fee of $19.99. So I know that $19.99 a month is what Anthony is going to be charged. The end of the problem tells me that we are dealing with N months. Therefore, if it's $19.99 a month and there's N months, algebraically, I'd write that as $19.99N. I look at my answer choices and I say to myself, wait a minute, there's a couple of them that don't say $19.99N. They're putting the N elsewhere in places it doesn't belong. Which ones? Well, your eyes might have caught that C and D are not showing the $19.99N I would like to have. They're out. They're gone. I'm never going to worry about them again. Then, what's the next easiest thing I see? Well, the additional graduation fee of $15 is charged every time he moves up a belt level, and he moves up 2 belt levels. Well, that's pretty simple. He's going to take that $15 times 2 belt levels is going to be $30. And the problem doesn't say that anything special happens with that number. He just gets charged it additionally. So I know that my right answer here should be $19.99N plus 30. Well, if I look at my remaining answers, choice A is attempting to apply some other number to that $30. That's not what I want. It's just supposed to be an additional tacked on fee. There goes A. My answer is B. Something to note here, maybe the scariest part of this problem was the tax of 7%. I wound up never needing to deal with that. And it's all because I worked the problem in bite-sized pieces. So another concept then is whenever you do bite-sized pieces, you often want to apply the process of elimination. After every step you do, is there an answer that could now be exterminated from the problem? As you move through the test, you're going to see all different types of math show up. And it's always going to be tempting to try to take in all the math at once. But you'll see that if you break that math apart, you're going to catch patterns or shortcuts you didn't realize were there. Take a look at this next problem. Once again, it's a word problem. I'm ignoring all the text and going to the final question. What's the product of all the numbers that are elements of set A or set B? This is going to be a pain, but it's going to be better if I deal with one set at a time. Let's start with set A. The problem tells me that set A consists only of fractions with a numerator of 1 and the denominator D such that D is between 1 and 8, not including 1 and 8, where D is an integer. Oh, Okay, so the numbers between 1 and 8 are 2 through 7. So we're talking about 1/2, 1/3, 1/4, 1/5, and 1/6, and 1/7. That is set A. Set B. Set B consists of the reciprocals of the fractions with odd denominators in set A. So even if I'd accidentally started with set B is telling me, hey, slow down. You should go back and start with set A first. So what is set B? It's all the reciprocals of the fractions with odd denominators in set A. Well, the odd denominators in set A are 1/3, 1/5, and 1/7. What's the reciprocal of a third? I believe it's 3. What's the reciprocal of a fifth? 5. And what's the reciprocal of a seventh? 7. What does the final question want me to do? Take the product of all the numbers that are elements of either of these sets. But I noticed something. When I go to do the product of a third and 3 of any number in its reciprocal, what do you get? You get 1. So a third and 3, when you multiply them because you're doing product, cancel. A fifth and 5, when you multiply them, cancel. A seventh and 7, when you multiply them, cancel. All of this crazy work literally works down to 1/2 times 1/4 times 1/6, which in my calculator or even on my own gets me 1/48. Is that an answer? Sure it is. It's choice B. So notice on this problem that the initial look here is that this looks crazy. There's a lot going on. There's 2 different sets. It looks like your calculations would take forever. Starting with the most straightforward piece of information, what the problem tells you kind of needs to be the starting point in this case, helps you really, A, slow down and work one step at a time, but B, make a lot more progress than you would if you looked at everything right from the beginning. Even when the problem tries to introduce many different unknowns, it is still going to be in our interest to go one step at a time on a word problem, always starting with the last question. This problem wants to know that if one day she mixes both green and orange and uses equal amounts of red and blue paint, right? What fractional part of the paint that she uses is yellow? I'm given an important piece of information here. This artist wants to make green and orange, and to do so, will use equal amounts of red and blue paint. Let's see where those things first come up. To make green, she's going to mix blue and yellow in a ratio of 3 to 4. So I could say that blue to yellow is a ratio of 3 to 4, and that's when the artist wants to make green. So far, I only have 1/2 of my final problem. I know she wants to make green and she wants to make orange. The next bite-sized piece, she wants to mix orange by doing red and yellow. Red and yellow in a ratio of 2 to 3 will make orange. Now we know she's going to make green and orange, so I need both of these equations. But notice how it says she wants to use equal amounts of blue and red. Well, right now, my amounts of blue and red are not equal. What could get them equal? Well, it looks like that if blue is my 3 and red is my 2, I could perhaps multiply the first ratio by 2 and the second ratio by 3 to make my blue and red amounts be equal, one step at a time. 2 times 3 would give me a blue value of 6. 2 times 4 would give me a yellow value of 8. On the second equation, 3 times 2 gives me a red value of 8, and 3 times 3 gives me a yellow value of 9. Now, is she mixing green and orange by using equal amounts of blue and red? She is. These are the equations for green and orange, and we have made blue and red equal. So, how can I figure out what fractional part of the paint she makes is yellow? There's 6 parts of blue, 8 parts of yellow, 6 parts of red, and 9 parts of yellow. When I add 6 parts blue, 6 parts red, 8 parts yellow, 9 parts yellow, I get that the total here is 29 parts. The yellow components are the 8 and the 9, which add to 17 parts. Since I want a fraction, yellow would be 17 of the 29 total parts needed to make green and orange. What is the answer? It's answer choice B. Try to imagine the opposite. Try to imagine if you read the problem right from the start. Your brain would try to combine these numbers so many different ways that it could be very easy to lose sight of one of the most important pieces of the problem. That at the end of it all, red and blue need to be equal. And that gives you your insight as to how to catch things. Now, you've noticed up here that this problem involves a calculator. Many of the problems that are these longer word problems or data analysis problems encourage you to use your calculator. That's not going to change the fact that you want to work the problem one step at a time and only use your calculator when you need it. Now, one thing you'll see with these problems is that sometimes there'll be kind of like an introductory piece and then several problems based off that introduction. Where do you begin? Yes, of course you want to read the introduction, but first you want to know what the final task from your problem is. After 20 hours, how many more microbes will bacteria B culture contain than bacteria A? That means I need to calculate, right, the bacteria B and the bacteria A. And on the surface, that could be a ton of work. However, maybe not. I asked myself, where do I want to begin? Well, it might help understanding how the bacteria A culture is growing. If we look up top, the growth of bacteria A is modeled in the equation n equals 200 times m to the h, where n is the number of microbes and h is the number of hours. Now, I am told some pieces of this formula. First of all, the rate grows at 10% every hour. So every hour, this amount needs to get 10% bigger. Then, they tell me that n is the number of microbes. Okay, that's the number of microbes I'll get at the end. H is the number of hours. Well, the problem told me that I'd be calculating this after 20 hours. Oh, well, that's something I can work with. If I take the equation then, n equals 200 times the number of hours, which is 20, I've come a long way towards figuring out what's going on with bacteria A. Then I have to deal with the m. Now, if something is going to grow 10% each hour, it needs to at least keep the initial amount, we'd call that 1, and then also grow by 10%. Well, at this point, just like I'm going to do, we would be taking out our calculator. We're going to do 1.0, right? We're going to raise that number to the 20th power. We're going to multiply by 200. Now, we wind up getting a rather large number, right? We wind up getting 1,345.49, roughly. That's okay. It's fine because what I've done is made sure that I'm only working one piece at a time. Now I'm ready to do B, and watch how much more quickly I can do the pieces for B now that I've done them for A. For B, it says it's the same formula. After all, the two cultures begin at the same time with the same number of microbes, so N would equal 200 microbes, but B grows at 15% per hour. That would be 1.15. Since they begin at the same time and they run for 20 hours, now that would be raised to the 20. So I'm going to take 1.15 in my own calculator. You can follow this along. I'm going to raise that to the 20th. I'm going to multiply that by 200. And I'm going to get 3,273.30. Craziness. But now all the question wants to know is how many more will one contain than the other. I'll take my first result minus my new result minus my original, and I will get 1,297.8. Notice the question, round your answer to the nearest whole number. So that looks like instead of 1,927.8, I'm looking at 1,928, and I'm bubbling in the corresponding ovals. It's a lot of work to be sure, but the last thing I want to do is have read this novel and then start wondering what the math is. I am going to be so overwhelmed by what's going on that any chance of breaking this down on the bottom, it's not looking so hot. You know what I mean? So, there's one example of how important it is. Don't try to do two things together. It's always going to be one thing at a time. Okay. It's not just going to be about long, complicated math. Even when you're dealing with relatively simple dollar amounts and arithmetic and regular additions, you'll be happy that you break things down this way. So, if Kelly and Brandon rent a beach umbrella for 2 weeks instead of renting one each day for 14 days, how much money in dollars will they save? Once again, you should say, this problem looks a lot more simple, but there's nothing different about it from the previous problem. I have two scenarios to work out. I want to do one at a time. What looks simpler to me is simply if they were to rent a beach umbrella for 2 weeks, and I know that it only costs $28 per week. Well, look at this calculation. It's just 28 times 2, which gives me 56. What else do I need to work out? Well, what if they do that? Instead of renting one each day for 14 days, the problem tells me that's $4.25 a day. So I take this $4.25 and I multiply it by my 14 days. Once again, we have a calculator symbol. There is no reason to make a mistake here just because we were going too fast. And I get 59.5. So how much money in dollars will they save? Well, they will save $59.5 minus $56, and they will essentially save $3.50. Problem says to leave off the dollar sign when gridding, so I can put in 3.5 or even 3.50, it won't matter, and I've got my answer. Pretty straightforward, right? It's just that when I read it first, the overwhelming odds that I do some unintentional math that isn't necessary for the problem wind up increasing quite a bit. And you know what I'm talking about. Look back on a previous SAT or some practice you've done. Have you ever had those problems where you basically have like a mountain of calculations and you actually add your answer several steps in? It's frustrating, right? And Bite-Sized Pieces is here to save us from that frustration. Now, most problems we've looked at tonight, they've been word problems. But not every multi-step problem on the SAT is a word problem. All it means is it's got to have multiple calculations. And every time you have a problem with multiple calculations, you want to consider the possibility of doing things one bite-sized piece at a time. 2 times 4n cubed minus 2n squared plus n plus 8, close parentheses, minus 3, open, times negative 7n cubed, out of breath already, plus 2n squared minus 5n plus 9, close parentheses, equals. And I see that my answers contain one of each of those terms. You might be watching this and literally rolling your eyes. How many times have you had to distribute and combine like terms in your life? It's probably getting ridiculous at this point. We'll combine like terms too, but I'm really interested in the fact that all of these have a single n cubed term. And that's where I'm going to start my work. The first n cubed term I see is to distribute 2 times 4n cubed. That would give me 8n cubed when I multiply. The other n cubed term I see is negative 3 times negative 7n cubed. Multiply those, I get positive 21n cubed when I multiply. The problem wanted one single n cubed term. I combine these to get 29n cubed. If you remember from before, I hope you're looking at these answers right now and you're begging me to notice what you've already noticed. That choices A and B, by offering me negative 13n cubed, it's the wrong coefficient for n cubed. A and B are gone. And just like that, we're most of the way home. What's the next term I see? N squared. So 2 times negative 2n squared is negative 4n squared. Negative 3 times 2n squared is negative 6n squared. There needs to be one n squared term. Negative 4, take away 6 more, gives me negative 10n squared. Well, between these two answers, plus 10n squared won't do the job. This time around, my answer just has to be D. I never needed to deal with the n. I never needed to deal with the 11. They just wind up being totally irrelevant. Your high school math instructor might really have wanted you to show that you can do every step of the work. But ask yourself this question: is anyone ever going to look at your booklet? No, they're pretty much just locked in a vault somewhere. Can you show College Board your booklet and try to get partial credit? Again, nope, locked away, not possible. So why are we doing all of the work? And why are we trying to understand everything in the problem right from the outset? Because that's what works in high school. But hopefully by now, if you've been following us each week, this exam is a different beast. It's a different animal. The same rules don't apply. So when the College Board tries to give me some monumental task to sink my teeth into, whereas someone else might want me to chomp, I'm going to nibble. And we'll move on from that eating analogy if it gets a little bit uncomfortable for you. Just make sure that when you're given any type of complex calculation, thinking back to everything we looked at tonight, you are saying to yourself, what is the most straightforward piece, easiest piece of information? And let me start there. It's very much the same as if you were about to put together a 10-page paper. You might start by coming up with a thesis or writing an outline. Why? Because they're simpler. The thesis gives you direction. The outline helps you break things down. And we want to just take that same thought process and apply it to the SAT. Bite-sized pieces, along with reading the final question and eliminating answers as you go, is one incredibly valuable and powerful math section technique you can use. And I really hope that it helps you succeed that much more on this exam. Listen, guys, thank you so much, as always, for joining Princeton Review on YouTube with SAT Night Live. We're here almost every Wednesday at 7 p.m. Eastern Time, breaking down the standardized tests, making them less scary. We are always here to help you out. Have a great rest of your evening, and we will see you guys next time. Take care.